here today, not only because of the beautiful program that our organizers put together, and I'm really excited about that, but especially because this is the occasion of Eduardo's 60th birthday, and Eduardo is one of my oldest and best friends and collaborators for more than 30 years, so this is a fantastic occasion. I'm really glad that I was able to be here and to share my joy with Eduardo. So here's a picture we actually took last week when we visited Eduardo in Campinas, and it just shows how great friends we all are. And I would like to say a few words about the history of our friendship and our collaboration, and also about what he contributed to Brazil. So we first met at Rutgers when he was a graduate student of Piers Coleman, as we just heard, and I was a postdoc just looking for a job, and this was a very challenging time, but at the time we were friends and we went to lunch together. We discussed often, but we didn't actually collaborate. Eduardo went to Florida a year before I left Rutgers, and he was studying as a postdoc there with Bob Schrieffer. But then I came a year later, and my main interest in life was the mental insular transition and some effects of disorder. And when I came to Florida, Eduardo pointed out that similar physics and relevant physics is found in his field, and he was working at the time on heavy fermion systems with Piers Coleman, and there were some significant effects of disorder, and he proposed that we start our collaboration, and we started to work together. We never stopped. This has been almost 30 years ago, and it has been a great fun for me, and I think I learned a lot from Eduardo during this process. So this initial collaboration was fairly successful. Eduardo got a number of invited talks, and he was a hot star, one of the young stars in the field. And I was asking him, well, are you going to look for a job in the United States? He said, well, probably not. I said, why not? You should be very competitive. Well, he said, you know, he wants to go back to Brazil. He wants to help Brazil and help build science in Brazil and help his country. He really felt very patriotic, and he felt that he had to contribute. I was very impressed by that. Eduardo returned to Brazil. I don't know if we will ever see each other again or whether we'll continue collaborating, what's going to happen. But amazingly, we continued to work together, and I'll say a few words about this. But before I say that, when we were still in Florida together working on disordered condo alloys, these are characterized with broad distribution of energy scales, rare events, and so forth. And Eduardo noted a similarity to random spin chains that Daniel Fisher and many others have been working on. He was very impressed by that. I was very skeptical about this. I said, Eduardo, you're wasting your time. This is going nowhere. Well, I could not have been more wrong. And he said, well, you know, Vlad, I'm not going to listen to you. And so he continued to educate himself in this direction and to work on this after he came back to Brazil on these random spin chains. And lo and behold, several years later, it turns out that he has panned out in many ways, not only because he educated some wonderful people that I'll mention in a few minutes, but also this field expanded, and it turns out that the relevance of these ideas was really far-reaching, and later we together realized that this is also of great relevance to the problems that I was primarily interested in, the mental insular transition and non-Fermi liquid behavior caused by disorder. So this has been very influential for me, and I couldn't be happier that I was wrong in my skepticism, but Eduardo really took the lead and charted this direction, which has really been a lot of fun and as well as fruitful. So Eduardo, after he returned, he had a number of excellent graduate students. I will not speak about all of them. I know that there are more. I will just speak about those that I collaborated with, and in fact, over the years, I was very fortunate that many of these students and some of them postdocs were going also to the United States and spent some time in Florida as well. And I had a chance to work with these fantastic people who actually all turned out to be very successful. And this is a real delight to see that how all this panned out. The first one was Carol Ogiar, who came to Florida and spent a year on an exchange program. We worked at the time on disordered Haber models. Here is one of her slides. And this picture over here, is there a pointer? This is a pointer. Yeah, this picture is actually several years later, or maybe 10 years ago, when I visited Carol in Belo Horizonte. Carol went on to Rutgers, actually, to work with Kotliar and Abrahams, and we continued our collaboration later. And for a number of years, this has been a lot of fun. Here is one of her phase diagram. For the first time, she was able to combine the mod physics with Anderson localization, and we had some predictions that later turned out to be of relevance to experiment. What's most amazing is that Carol is now a very successful professor and has a huge group, much bigger than mine. But one of her first students was Elena Berganza, who actually also collaborated with Carol and me on a project more recently. I think we had a paper in 2015 or 16. And now Helena, who is shown here, is in fact a professor on her own in Brasilia. So this is really a delight to see all these people so successful, and we continue to talk and be great friends. Some of them, including Carol, have become, of course, taken new directions, and but we continue to talk. The next student was Eric Andrade, who spent, I think he was in Florida in 2007, 2008. And this was the time when these ideas from rare events and quantum Griffiths phase, it turns out, popped up in the physics associated with disorder effect on metal-insular transitions. And Eric, in fact, during this period, discovered this quantum Griffiths phase, which was really surprising. It has many analogies to the physics that Daniel Fisher and later Thomas Vojta and Jose Hoyos discovered in magnetic systems. Here are some beautiful pictures that Eric produced. And Eric, based on this work, he later went on a very successful postdoc with Matthias Vojta, who really expanded his horizons, and now he's a very successful professor in fact, here in São Paulo. We are already continuing our collaboration, and in fact, I spent 2 weeks with Eric just before this conference. It was a real delight to be with him and his charming wife and to talk excellent science. So the next person that Eduardo educated was, or I don't know if I missed some, but that I'm familiar with is Jose Hoyos, or so-called Manaus. I know many stories of two of them working together from both Eduardo and from Manaus. I know that one of the big failures of Eduardo is he educated him in rock and roll music, but he never educated him to drink caipirinhas. So you can't have everything, right? Manaus still refuses to have caipirinhas. But he's a brilliant physicist, and at some point, I think when he was a postdoc, we worked together on random magnetism, and ideas from these flow equations, the strong disorder RG, turns out to be very successful and describe some physics on the insulating side of phosphorus doped silicon in a very elegant fashion. He really contributed significantly to this. And later, we also worked on using similar ideas to disordered electronic systems to Anderson localization, which was to develop a totally new approach. So Jose was instrumental. And in fact, my own graduate student from Florida was sent to Brazil, and he spent a year, I don't remember when exactly that was, maybe in 2011 or 12, and spent some time. I think it was 6 months with Jose, who educated him and helped him along. So that was fun as well as really successful. And then the next student was Marta Villagran, who worked on another set of problems. She worked on effects of disorder on the phase coexistence between a metal and an insulator. There is some really nice physics. I believe that, in fact, tomorrow Eduardo will speak about some of the latest results along these lines, where we found some strange behavior of domain walls. You can see here, you can see domain walls between a metal red and insulator blue, and these domain walls have some really unusual properties. I think Eduardo will speak about this tomorrow. So now Marta is continuing her career in physics. She's in Texas, University of Texas, I think at Houston. And we communicate every so often. We finished some of the papers together that were initiated earlier just recently. And finally, the last person that I collaborated with is Victor Quito, who spent a couple of years as a postdoc in Florida working on problems related to phosphorus doped silicon, as well as several other topics. And now, then he moved to Iowa to a very nice group of Rebecca Flint, and he had a great time, very, very productive, and this was rewarded. He was just hired, I understand, in San Carlos, where he joins Jose and at one of the top institutes or universities in Brazil. So it's amazing to me how many what was the gigantic impact that Eduardo had on the Brazilian science, and I'm glad that I was able to be part of it and to really get to know all these wonderful people and to continue our friendship and our collaboration. So this is about science. I cannot talk about all the projects that we worked together and everything that Eduardo did without me, but I just want to share a few more pictures over the years. We have many shared memories. We kept going back and forth. He visited Florida a number of times, and we also met in many conferences. Here's Leiden, 2005, where here's Eduardo with Boris Spivak. That was a really fun conference. And then in Dresden, where Matthias is now, and here is 5 years ago when we're at the same conference, 5 years ago before COVID, which seems like 100 years ago now. and we are here. We are sitting with our friends from Switzerland and Oscar from Florida. So those are some shared memories, but I should also say that Eduardo, especially in the early 2000s, he spent significant time in Florida, and at the time we had some money for visitors and so forth. So he actually spent quite a bit of time, and one of those times he in fact spent, I don't know how many weeks or months, or I don't know, a lot, in my house. With us, our son was very small still, and he just loved Eduardo. But we had a great fun. I mean, I drove him crazy. I would wake up in the morning. I said, Eduardo, I just have to tell you this, and then until midnight. And just let me tell you this. I said, Vlad, don't you ever get tired? Why don't you just relax? No, Eduardo. So I couldn't stop. We had a great deal of fun. But I discovered at the time that there were some serious gaps in his education and in his knowledge. And I decided, together with Vasily, our son, to contribute to this and to educate him and to make him a better man. So what I discovered is that he didn't know anything about Star Wars. And we couldn't believe it because Vasily and I and Dragana, we are big fans of Star Wars. And so then we decided we had all the DVDs, of course, and we started to play all the movies one by one. And, some of them, you know how it goes, episode 4 or 5. But I remember vividly when we got to that point where Luke was fighting with Darth Vader, and then Eduardo was like, you'll see for yourself. I mean, this is not exactly the picture, but you see when Luke says, Luke, I'm your father, and Eduardo was like, whoa! So this is my modest contribution to Eduardo's education and completing his knowledge. So this has all been a terrific fun, and I'm really fortunate that I had such a great friend and colleague and someone I really cherish and admire and respect a great deal. So it's wonderful to be here, that we all celebrate his 60th birthday. And I hope, we've spent 30 years working together and being great friends. I hope for another 50 years of that, hopefully. But we are here to celebrate, and so let's just congratulate Eduardo for his 60th birthday and all his great accomplishments in science, as well as really completely changing the landscape of Brazilian physics.
Our next speaker is... Keep going.
So now I will, you know how they change the face. There are people who have two personalities, from nice guy to scientist, right? Okay. So now I will hopefully be able to tell you about some very recent work that's been very exciting, and in fact, a work that's very closely related to what Oscar described. In fact, I was quite a bit influenced by Oscar and learned from Oscar, and I always ran to him for advice and for consultation when it comes down to this, because it is about moiré materials, which are a fantastic new platform. But I would like to tell you how somehow this is really part of the big program that I've always wanted to develop, and it turns out very close to my own interest and super useful. So the problem that I wanted to solve, well, let me tell you an anecdote. When I was at Rutgers, this was the heyday of high TC. Just high TC, a few years after high TC, but Gabi Kotliar, my boss, told me, Vlad, if you work on high TC, superconductivity, you will never get a job. Oh, I said, Gabi, what should I do? Well, you should work on fundamental problems in physics. Well, tell me what to do. Well, it says one of them is the metal-insular transition, and that's never going to go away. And so I decided to work on this. In fact, I started already to work on this before that with Ted Kirkpatrick, but this was a time of great discovery, and it became clear that this is really a confusing problem, because we know what metals and insulators are. They behave differently at low temperature, but if you can tune from one to the other, there's an intermediate region which, well, some people call it quantum criticality. It doesn't matter how you call it. It's something that's neither one nor the other, and we want to understand how it works. It's really important because what is solid-state physics? It's about electrons moving or not moving. Okay, so now if we set aside processes where you can change this behavior by breaking symmetry, which has been well understood for many years, at least in principle. But I would like to focus on phenomena where you can change the dynamics of the electron by in systems where you don't change the symmetry across the transition. So there were two great minds in the early days. Mott said that interactions can do it. Anderson, disorder. How those do combine together? That's been a very difficult and long-standing problem. And part of the reason is because there's a lot of controversy when you do experiments, how you can tune systems and whether you are really seeing what you want to see. And so experiments presented a lot of limitations, and this field slowly died off after the 80s and 90s. But there's been a tremendous boost to this field with this new discovery that these moiré materials came up in 2018. And the first discovery was associated with graphene bilayers that we heard about. They're extremely sophisticated and subtle systems because topology plays a great deal as well as very strong correlations. So I'm not going to speak about this. And I thought this is not for me. I mean, I tried to solve simpler problems. But then a few years later, my wife said, why don't you listen to this online talk by Jia Shan? I was like, this was COVID, and I was like, oh. I said, okay. And then I discovered that there's another class of materials, transition metal dichalcogenase-based materials. So here is one of them. With two different layers, and then you can also get narrow bands. But it turns out in these systems, these are better model systems to a platform to study a single band model with strong correlations. So a lot of the physics that we try to study is really beautifully realized there. And amazingly, in these systems, you can change the band filling, but also the band width. You can see here two band structure calculations that this band can be broad or super narrow, and you can experimentally do this by applying voltage on the front gate and the back gate, and then you can change, as it turns out, independently the band filling and the bandwidth. So here is a map, or a resistivity map of this device when you tune these two voltages, and you can see red regions are high resistant regions. This one is a half filled band, this one is a full band, and there are other fillings. So you can actually move, you can tune these voltages to stay at a fixed filling and change the bandwidth, or you can change the doping at fixed bandwidth. So this is really an amazing thing that could never be done before. And these people devised also some really extraordinary probes, excitonic sensor. You can measure the spin susceptibility and many things. So this is really a completely different level of sophistication. And the immediate results that first came out were associated with studying. They had a paper where they studied the Mott transition at half filling, the problem that's been around for a long time. And it turns out that the results, which are shown here, so this was a paper a couple of years ago, a family of resistivity curves that they obtained, beautiful curves, show metal insulator transition from a nice Fermi liquid to a Mott insulator. But these results look almost identical to other platforms like Mott organics and even to the electron gas. So it turns out there's an amazing level of universality associated with this transition, even though energy scale here, the bandwidth is around 200 Kelvin, here it's about 2000, and here it's about 20 or 10. So you have many energy scales, but some very nice physics is found, and this is identified as physics dominated by strong correlations or Mott physics. I'm not going to talk about this today, I just want to mention it, but we have a little review article published recently that discusses, in fact, how similar the systems are and the level of universality that you find. I believe that we have reached some very good understanding because we can see now that there are some really robust features, but anyone interested can have a look over here. And, but today I will talk about some other regimes that are found in these materials. So again, here is the introductory slide, but now we are not going to look at this multi-insulator. So here is the half-filled band and the multi-insulator, the red region. You can also go to a partial filling of this band. And the most naive expectation is that if you are half filling 1 electron per unit cell, then strong repulsion can stop them from moving. But if you are partial filling, the lattice is not, there's not enough electron to block each other, to create this traffic jam of electrons, and so adopt multi-insulator typically are conductors. Amazingly, there is some interesting physics. There is some odd physics that has been uncovered, even away from at lower fillings, and I would like to just very briefly mention this here. So this is an old idea. In fact, that goes back to the history of the 2D electron gas, as well as early ideas of Wigner. And the ideas are that if you have lower occupation, you can form the electrons due to the long-range Coulomb repulsion. They can form a Wigner lattice, and then there is 1 electron per site still. So if you have on-site repulsion, which is strong, but these electrons are in potential wells produced by neighboring electrons, you can still have a multi-insulator. And this is, in fact, an idea that was put forward earlier. Like, I think one of the first papers was this one from 2008, that this should be regarded as a Wigner-Mott insulator. And this has been, in the 2D electron gas, quite speculative. But here, in these moiré materials, they can be done modeling, but the excitonic sensor has also mapped, I'm not going to explain how it works, but they were able to see insulating states at numerous fractions. At first sight, it looks like fractional Hall effect, has nothing to do with it. It simply has to do with the fact that there are certain commensurate fillings which favor periodic patterns forming Wigner crystals, and that exist, these special fillings will be insulating. So this has been very nicely seen by Shan and Mack here, and we wanted to contribute to this, and with Luke Rademacher, we now have a preprint on this physics. I'm not going to give you many details, but the point is that you can look for different periodicities and see how the energy or the free energy depends on filling, and you can see that at certain fillings, certain patterns are favored. This is not a surprise. Well, we also found that if you don't have commensurate fillings, for example, a half filling, then near half filling and many other fillings, you can also find that the free energy has metastable minima, which are amorphous. This comes as a huge surprise, but at first sight. But it turns out that actually in other systems, people have established that metastable state of the glassy nature, amorphous states of electrons have been in fact experimentally observed. And perhaps it's not a surprise that over here, you see this purple band indicates the free energy of these metastable states. So you see in some places they are higher in free energy, but they will be favored by entropy and by impurity. So we are proposing in that paper, I will skip all the details here, but we are proposing that, across this phase diagram of Wigner-Mott states in the moiré materials, there should be also competing states which are amorphous with some very bizarre properties, which we studied in the paper. I just want to mention briefly that this is not a particularly rare event. In theta organics, which are quarter-filled quasi-2D triangular lattices, they have found that, so you have every other site is full, every other site is empty. The ground state is stripes, and there's a first-order transition where stripes melt. You can supercool it, and then there is good experimental evidence from Kanoda that you form some amorphous state. They have dynamic evidence of this, and as well as X-rays. And we have actually written this paper in 2015 showing that this can be modeled and that this is very reasonable. This is something like a striped glass that Jörg Schmalian and Walliness proposed many years ago. Even more amazingly, it turns out that in transition metal dichalcogenide, quasi-2D materials like this one, charges will form this periodic pattern. This is polaronic crystals of Star of David polarons. You see it's a perfect triangular lattice, which some people believe it's a multi-insulator. But what Dragan Mihailovic has done, you can blast the laser and cool it quickly, and then this beautiful lattice turns into this amorphous lattice, which is very robust. So it turns out there are competing amorphous states, which can be really seen not only through kinetic measurements, but in STM. You can really see how metastable amorphous states can arise due to the combination of strong interactions and lattice frustration. So this is now an emerging field. We heard something about this on Monday. But Dragan Mihailovic and Ljubljana pointed out that, in fact, there's this gigantic family of materials which all show this kind of behavior. Again, something similar to what was proposed for moiré. They are commensurate fillings with periodic patterns, and this purple band is competing amorphous states. So there's now very good experimental evidence that this is reality, and we proposed very recently that this is also relevant for some moiré materials. I will not say more about this, but I would like to now move to the main topic of today's talk, which is that, amazingly, we are not going to, you cannot only study this mod transition at half-filled bands, integer filling, shown here, which I mentioned just before, and that looks very similar to the mod transition in other platforms like mod organics, almost identical. I'm not going to talk further about this, but I would like to notice that in the paper that was published in Nature in 2001, they focused on this transition here. But in the appendix of the paper, or supplementary material, they also show that there is another insulating state here when the narrow band is full. So not half full, but full. And then you can, by tuning the bandwidth, you can close the gap, open or close the gap between the narrow band and the other bands. So this is like a band transition. And they've shown the resistivity curves. Here are the resistivity curves. In fact, in that paper, there are not enough curves, so they were kind enough to send us some more detailed unpublished data, and these are the unpublished data that later came out in our paper. But these are the curves, and at first sight, they look very similar. You just go from metallic and insulating, but a closer look reveals some very interesting features, which are qualitatively and significantly different from the mod scenario. By the way, I want to mention that that mod scenario I showed just before is very consistent with all possible predictions of DMFT, and which is a super simplified theory, but I've spent quite a bit of time now with Martin Dressel and other experimentalists to check the predictions of various theories and against mod organics, and moiré is very similar. So I think we understand this pretty well. This is something totally different. So let me walk you through, show you some relevant features of these families of curves. The first thing you notice that there is on the metallic side linear resistivity. Now this is over a very broad range of temperatures. Note that this 200 is roughly the bandwidth of the narrow band. So this is a broad range of temperature, it's linear, and it's more pronounced away from the insulating side, which is very different from the proverbial strange metal or Planckian metal, which you see only close to the insulating state. So this has to be a completely different reason, and this immediately reminds you, this is almost like a half of the bandwidth. So this reminds you of phonons, linear resistivity due to phonons, and it's quite reasonable. In fact, Oscar helped me with this. There are estimates you can make. There are some soft phonons in these materials related to vibrations between the two layers, and it's reasonable to have that there are some bosons that can scatter incoherently and give you linear resistivity. So this is what you see on the metallic side, but as you approach the insulator, the range over which this linear resistivity survives actually decreases, and it's shown here by T star. So if you do a detailed analysis, you see that this range of temperature below which T star is linear, it shrinks and vanishes at a particular point. You can also look at the conductivity extrapolated to zero resistivity, or the conductivity at zero temperature, and you see here resistivity rising. The conductivity, corresponding conductivity, decreases, and it whoop, what happens now? Shake, rattle, and roll. The conductivity decreases and extrapolates to zero exactly at the same point as this T star line. You can go to the insulating side, and you find that you have activated transport, indicative of a gap opening, and the gap closes as you approach the transition from the other side, again, at the same point. So it looks like there's a sharp transition where various energy scales vanish, which is exactly what you expect for a continuous transition. And then, in addition to this, you can notice that this linear resistivity has a positive slope, like it always does in metals. But as this intercept goes up to become more and more insulating, this slope, in fact, changes sign, and you see a characteristic fan shape of curves here. So you can plot this slope versus as you approach the transition, and you can see that it initially goes up, and then it changes sign and goes down. So this change of slope of the resistivity is another prominent feature that caught our attention. So those are very nice features, which, as it turns out, I immediately recognize are what you see in many, many other examples of disorder-driven transition. So let me just mention, this is very important in my mind, because when I was a graduate student, my Bible was the Lee and Ramakrishnan review article on disordered electronic systems, 1985. And they mostly talk about weakly disordered metals, which were understood pretty well at the time. Another transition was still mysterious. And at the end of their article, they talk about open problems in the field that they would like someone else to address. And one of them was that in many, many disordered materials, which like amorphous alloys and other materials, phase-changing materials, for example, you see metallic behavior on the metallic side, then you can damage them with irradiation, with high-energy ions or X-rays, and then the residual resistivity grows, but the slope changes sign, like this. And this was first discovered by Hans Muy in 1973, later documented in a number of materials. There is a linear relationship between the intercept and the slope shown here. So this is called Muy correlation, and it is something inconsistent with the so-called Mathiassen's rule, which says that if you have weak scattering, then elastic and inelastic scattering should simply add up, and the curves should be simply shifted up rather than changing slope. So this is the breakdown of the Mathiassen's rule, and amazingly, this happens exactly at the Mott-Joffe-Regel limit, where the mean free path is of order of the lattice spacing. So this phenomenon, so notice that this is still a conducting here on this side. So this is not a metal-insulator transition, it is something that happens before the transition. And amazingly, this is seen in this gigantic class of all kinds of alloys. So this is a very common behavior, which we now saw in moiré materials. So I said, wow, it looks very similar to disorder-driven transitions. Another prominent feature in, for example, here shown compensated doped semiconductors, but also in amorphous alloys, niobium silicon by Dines, Hertel, and this was Dines. You can see as you approach the transition, the low temperature conductivity decreases and linearly goes to 0. Just like we saw for moiré. Now, why is that in my mind so a smoking gun? Because the non-interacting picture of Anderson localization is well understood, and it has a critical exponent 1.6. Percolation, semi-classical percolation, would give you 2. So according to these two scenarios, which are well understood, this transition should be approached with 0 slope, and you have to be blind not to see the difference between these two, right? You see that this is totally different than Anderson localization or percolation. So it has to be, because Anderson localization, you just put impurities and you solve the problem. You can do it numerically. Today we know the answer. So this means that this cannot be non-interacting or weakly interacting. This is in fact all interactions. And finally, people have done transport early on in all times, but today we can, how much time do I have? 5 minutes? Okay, I'll go quickly. So just be patient. People have seen STM, done STM on all kinds of materials, and you always see gap opening. So let me go a little slow. So Anderson said in his Nobel Prize-winning lecture that in fact interactions and disorder can help each other, and they can help produce something completely different. So how can this happen in principle? Anderson said in this early paper that occupied states, when the electrons are sitting in bound states, they will affect the neighborhood, deform the neighborhood, and be shifted down. And this can open a polaronic gap, which is seen in many other instances, if you have strong disorder and insulator. Now, a simplest theory of this can be, the simplest toy model is just the disordered electron phonon model, which is given, which we discussed in this early paper. And it turns out that you can write down the simplest theory for this, which is a self-consistent theory of polaron formation and of disorder, the so-called CPI-DMFT. And what this theory shows is that the distribution of disorder becomes bimodal, and that helps open the gap. I'll skip the details, but we can apply this idea directly to the moiré system, and here is an example of a two-band model where we can tune the bandwidth so we can open or close the gap between this narrow band and other bands. Some pockets can be calculated, and you see actually in this case you don't even need really polarons to do this, but we need phonons or bosons to explain the temperature dependent of the resistivity. So this is a model of disordered electrons interacting with some dispersionless boson that we put in. It doesn't matter what is the physical nature of this boson. And now, let me show you the result of this theory. Well, you see, this is the experiment, this is theory, and I already walked you through this. All these features are perfectly well captured. This is the residual conductivity, the T star range of linear resistivity. You see that the slope changes sign before the transition is shown here, the Mui point, and the transition itself is over here. So all these features are perfectly captured, which is kind of amazing. I really didn't expect, but it seems to work. It's a super simple theory, and it seems to work. You can do even more. You can, in fact, scale the data as you expect for a critical point. You can, so this is, if it is a continuous transition, then this family of curves should be collapsed in a scaling way, and the scaling function we computed from theory is compared to experiment without any adjustable parameters. It works perfectly well, and this is the color code of the theory curves, which again shows the fan-like shape and the critical behavior, which is, as it turns out, confined to a rather narrow region past the Mui point. These curves can be scaled approximately in a much broader region, but that there exists a really quantum critical region in this theory. So this is what I just wanted to say, but I just want to say something else. That, you know, generally in theory, people have studied the metal insular transition was difficult because we didn't have a symmetry breaking idea to work with. And so people approach from 2 dimensions, and this expansion of stability of the metal in near 2 dimensions, this has been very unsuccessful. So this is why it's reasonable to go to high dimensions and approach the transition here, and this has been much more successful in statistical mechanics. So our theory is coming from up there, and I just want to mention that this simple, self-consistent, but strong coupling theory can be derived as a saddle point of a field theory. I'll skip you the details. You can look in, or there are some formulas you can write, but this is a standard way that people use in electronic disorder systems. You can introduce these Q fields, and you can write down an exact functional integral representation of interacting and disordered electrons. So this is not a big deal. The big deal is that when we do it for our model, the saddle point solution gives you exactly the theory that I just described. And this opens, in principle, a way to include systematic corrections to this strong coupling theory. And these corrections, this is known from the past, the Gaussian fluctuations will capture the so-called couperons and diffusons in other weak localization and other things that you may want to study. So in particular, in mean field theory, in Gaussian fluctuational mean field theory, we give you a so-called Landau-Ginzburg version for the spatial correlation functions that assume here a conventional form, and it turns out we can even determine the upper critical dimension. So I just want to conclude to say that in some other materials, people have looked at STMP images and look at statistics and correlations of these densities of states. And indeed, they find something very similar to what our Landau-Ginzburg theory seems to predict. So to conclude, I would like to mention that the moiré materials are a dream come true from someone like me. In particular, these TMD ones, which are much simpler than graphene, which is very solid, that Oscar discussed. That's probably too complicated for an old guy like me. But these TMD materials are pretty simple, and they're an ideal realization of many ideas from the past. You can study mod transitions, you can study Wigner mod transitions, but you can also study something which is more similar to disorder-driven transitions in these systems. And it seems that our strong coupling theory can describe all these regimes reasonably well, in fact, to my opinion, better than I actually was able to hope. But there are many open questions. One is, for example, this issue about amorphous metastable states. What is exactly their role? How often you see them? We just, I think, scratched the tip of the iceberg here, but as I told you, this is something that is probably quite common, not very well understood. It's a difficult problem to study theoretically, but we've studied similar problems using the replica extensions of DMFT in a sort of Parisi-like theory, and you can study this glassiness, and this remains to be done. Another issue that is of very relevance, we use the simplest Holstein model for these bosons that we put in. There are probably many physical realizations of bosons that play a similar role. Because you can have magnetic polarons, you can have lattice polarons, but you can also have the electronic polarons that Efrem Skolsky have discovered, or the correlation Hall. So all these things probably play similar roles, and it is a challenge for the future to incorporate all these in the theory and to see how robust are these phenomena. Glassy features that I've just mentioned here are probably prevalent near the metal insular transitions with disorder. Dragan Popovic over here has studied these for 20 years in some other systems, and now we'll talk about, in fact, some thermalization and pre-thermal regimes of MBL, which is also found in these systems. So I think there's a lot to do, and perhaps moiré can be an ideal platform to study many of these issues. Of course, probably the most exciting theoretical issue is to go beyond mean field theory, beyond this strong coupling theory, and to, while we have the theoretical tools now to perform loop corrections and perhaps build an RG approach, which should be relevant if we are able to experimentally look at a very close vicinity of the critical point. So I'll stop right here, and thank you very much for your attention.
Thanks, Vlad.
So Vlad, it's hard to believe there's anything we haven't discussed, but I think there is one thing that I would like to ask you about. If you go back to the first slides where it was a MOT-dominated systems, you had three different systems, very similar behavior.
Yes, yes, my favorite picture.
Right.
Yes.
So, yeah,
Okay.
there.
Yes.
So of course we have discussed the fanning there and the curves, you know, as they go, the metal and the insulator, but this downturn of the metallic curves, which seem to be present in all of them.
Yes, and so, you know, actually
this looks very much like a condo problem.
It is a very good point, Eduardo. In fact, you know, in DMFT, which can give you exactly this kind of family of curves, and it does, it is understood what this means. This is like Kondo, because in Kondo we are destroying a coherent band of quasi-particles, and we have a decoherence crossover. Near the MOT transition, this also exists, and this is when the temperature reaches a scale set by the characteristic energy scale of quasi-particles, just like in Kondo, which was first discussed by Brinkman and Rice. And in fact, this is called today the Brinkman-Rice line. In MOT organics, experiments have been able to detect this in several ways. One is from these resistivity maxima, but amazingly, you can see this actually in optical conductivity where the Drude peak vanishes. So we know from these optical measurements that this maximum is not something mumbo-jumbo, but it actually corresponds to this coherence temperature of quasi-particles. So this is now very well documented in MOT organics, and I'm pretty sure it's done here. There's another experiment that beautifully shows this, which is a now more recent work that we've done with Dressel also, where you can use dielectric spectroscopy, and you find that the electric constant is insulating like or positive but small, or of the order of 10, above this temperature, and below this temperature there is like a cliff. It suddenly zooms to a very large negative values characteristic of a metal. So this very sharp crossover that you see, and which is characteristic of, DMFT also shows this, which is characteristic of destruction of quasi-particles, can be really seen in the experiment very beautifully. So I think at least in those systems where this has been studied, there is no doubt that this is a incoherence crossover. And in fact, this family of curves, they all look, you see, the same if you rescale temperature by this maximum temperature. We have a series of papers now where you can actually take this family of curves, scale them, and it's particularly to the electron gas. There are 3 or 4 systems where this has been documented. The scaling predicted by theory works extremely well, including how the effective mass compares to the maxima, how it approaches the transition. So I think we have a now good understanding of this coherence destruction.
Thanks, Vlad. There is one short question that requires one short answer.
I don't promise.
I'm not particularly short, but Vlad, just a conceptual question about the Wigner MOT crystal. If I think in the usual Wigner crystal picture, right, I have 3 electron gases, but now they're in a lattice.
Yes.
So is it when I have a lattice and I use this mechanism, is it really that different than an insulating charge density wave that is forming, that is just changing the period of the lattice, or is there more than that?
Well, you know, this is funny that you asked that question. You see, in this very nice review article that Dragan Mihailovich wrote. So in this review article, I can give you the reference. He lists a huge family of transition metal dichalcogens. You see this charge density wave forming here, which is also then becomes a MOT insulator. But you know, in this community of these TMD materials, there's been a long-standing debate. Is this a Fermi surface instability, like a charge density wave, or it's mostly driven by classical electrostatics? And what Mihailovich points, he's on a crusade for decades to demonstrate that if you actually, because in quasi-1D materials, this charge density wave Fermi surface mechanism has been demonstrated in all kinds of details and works well. But in these materials, you can predict from this kind of theory that the characteristic wave vector of these charge density waves will reflect the details of the Fermi surface and what it should be for a given material. And this has been contrasted in this huge group with experiments. It turns out that this totally doesn't work, but if you do classical electrostatics, so you assume that these are classical charges and then ask when does this melt, that works really well. In some materials like these ones, this is because charges, these are very heavy polarons. And this puts the system automatically in the semi-classical limit. This physics has in fact been brilliantly pointed out in 2012 by Lev Gorkov, who wrote a single-author PRB paper in his old age, in his 80s, pointing this out. So I believe that all those examples that we are dealing with here are like a strong coupling version where it's not a Fermi surface, it is the interactions that dominate, and you can understand many features, including these metastable amorphous states, from the semi-classical perspective.
Okay, we have to move on. Thanks, Vlad, again.
Pleasure.